In example number 1, we're asked to find the exact angles of each of the trigonometric functions given the following information. So I would like you to do me a favor. I would like you to put in this particular angle, let's make this theta symbol. And so before I can answer these, I just want to remind you we have 3 primary trig functions: sine, cosine, and tangent. I purposely put these in a different order to see if you can pay attention to that. And then we have 3 secondary trig functions. The reciprocal of sine is cosecant. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. When we describe these trig functions, all we're doing is we're looking at 2 sides of a triangle and we're comparing it in a specific order. We're creating a ratio, a fraction to compare it. Let's get started. We need to know all the sides. Because it's a right triangle, I can use the Pythagorean theorem. A squared plus b squared equals c squared. Now these 2 are the legs. It doesn't matter which one. A doesn't need to be the shorter of the 2 legs. So I'm going to have a be 3. So I have 3 squared plus some value I don't know squared equals 5 squared. C squared is always going to be the longest side, which is the hypotenuse. Okay, so I have 9 plus b squared equals 25. So b squared, when I subtract the 9 to the opposite side, equals 16. I take the square root of both. Now here's the deal. This means you should get 2 values. You should have plus and minus 4. If I'm only doing algebra, I have a plus 4 and a minus 4. But remember, in this particular circumstance, I'm describing the length of the missing side of a triangle. And lengths are only described with positive values. That's why we keep it as just positive 4. All right, let's get started. So when I describe the sine of this angle, I'm looking right now at what is the opposite over the hypotenuse. And then I'm going to come right down here to the reciprocal of sine, the cosecant, and let's write down the reciprocal. Now cosine is adjacent over hypotenuse, so 3 over 5, and the reciprocal, which is secant, is 5 over 3. Lastly, tangent. Yes, we could say it's sine over cosine. That's one correct way to describe tangent, but another way to describe it is opposite over adjacent. So 4 over 3. And the reciprocal cotangent is 3 over 4. Now this looks a little more complicated. It's not a Pythagorean triplet. Those are pretty ones. They have no radicals involved. The 3, 4, 5s, the 5, 12, 13s. I need to figure out this missing length, and I'm going to do the exact same thing. A squared plus b squared equals c squared. So b squared is equal to 64 subtract 9. 64 subtract 9. So what do I end up by? I end up with 55. Let's take the square root of both. We know because we're describing this missing length is only going to be a positive value, but then I need to grab a calculator and I need to find out, can I reduce, that's the key, can I reduce the square root of 55? So I'm asking myself, are there perfect squares that nicely divide into 55? The smallest perfect square below 55 is 49. We can see it does not divide in and create that whole number. Let's try the next one. Divided by 36, that doesn't work. Divided by 25, nope. Okay, let's divide now down by 16, and we can see that none of these are working. You may say, what about 1? But 1's not going to allow us to break anything down. So we cannot break this down. Let's come off to the side and do the square root of 55. This time, I'm going to put the angle over here. And let's start again. Sine, opposite over hypotenuse. Opposite over hypotenuse. I go through the list and I find cosecant. Then the reciprocal of sine is cosecant. I'm going to write it as 8 over 3. Let's go on to cosine. Cosine is going to be the adjacent, so the radical 55 over the hypotenuse. Now be careful. When I locate secant, which is the reciprocal of cosine, I am going to initially write 8 over the square root of 55 because mathematically that's not wrong. It's just not the proper way to leave our answer. The proper way would be 8 radical 55 over 55. And lastly, yes, tangent can be stated as sine over cosine. The long way would be to take this fraction and divide by this fraction, but there's another way that we can achieve this answer. Tangent is opposite over adjacent, so 3 over radical 55. Again, that's not wrong mathematically, but the proper way is 3 radical 55 over 55. And you may be saying, like, why do you take time to write down 3 over radical 55? Because when I identify the reciprocal of tangent, I can see that all I have to do is flip this, and now it is already in proper form. All right, we're going on to the second part. Right now, this is lesson 1, right angle trigonometry, and right angle trigonometry is broken into part 1 and part 2. Part 1 is very procedural, part 2 is word problems. So on our first page, this is the second section of part 1. This is the only information I'm given, and I'm asked to then find the exact values of these 6 trigonometric functions. So here's what I'm going to do. I'm going to find secant, so go down below and find secant, and in that particular area, let's write down what we know. We know it's 3 square roots of 7 over 4. Now, I know that secant is the reciprocal of cosine. So I'm going to go right up to cosine, and I'm going to write down what the reciprocal is. I also know that cosine means the adjacent over the hypotenuse. So I drew a triangle, and I selected one of the 2 angles. It doesn't matter what angle, it just can't be the right angle. And now I'm going to place these numbers in the correct positions on this right triangle. Adjacent from this angle would be this length. Remember, there's hypotenuse and adjacent to help create this angle. Adjacent is a length of 4. Hypotenuse is a length of 3 square roots of 7. And now I have one missing side to identify. A squared plus B squared equals C squared. 4 can be either the A or B, it doesn't matter. 4 squared plus B squared equals, 3 square roots of 7 squared. I know 4 squared is 16. How do I write this out? Well, I'm going to write it out twice because that's what it means. We're taking the quantity 3 squared roots of 7 and we're squaring it. Okay, well, how do I multiply these? 3 times 3 is 9. The square root of 7 times the square root of 7 is the square root of 49, but I know the square root of 49 is 7. So this actually equals 63. I have 16 plus b squared equals 63. Now I'm going to subtract 16 over to the other side, and I'm going to take 63 minus 16 to get 47. I take the square root. Remember, normally we'd have a plus or minus, but we're talking about a missing length, which can only be positive. Square root of 47. There's one last thing we need to do. We're going to grab that calculator, and I just need to make sure this can't be broken down any further. So I know the first the first perfect square below this is 36. 6 times 6. Then I have 5 times 5. I'm just checking. I have 4 times 4. We can see none of these working. 3 times 3. None of them work, which means that this right now cannot be simplified any further. So how does that help me? Let's come back up here. What is the sine of this angle? The sine of this angle would be the square root of 47 over 3 square roots of 7. Uh-oh, we have a problem. What is the problem? Radical on the bottom. So what we're going to do is we're going to go times the square root of 7 times the square root of 7. Now on the bottom, I know this is equivalent to the square root of 49 because 7 times 7 is 49. And I know the square root of 49 is simply 7. So in the bottom, I have 3 times 7, which is 21. Perfect. I no longer have a radical in the bottom. How do I take care of the top? We're just going to take 47 times 7, so it's like combining like terms. 7 times 7 is the square root of 49. Well, 47 times 7 is the square root of 329. And before I finish this, I just need to make sure that it can't be broken down any further. So you're wondering, like, is there a fast way of doing that? Let's just try this. We're going to take this and divide this by, let's try right now 15 squared. It doesn't work. Let's try now and go divided by 14 squared, because that would be perfect squared. We're going to divide by 13 squared. Let's just keep going here, 329. And some of you may already recognize that we have a prime number, but you just keep going all the way down here, just making sure that none of these perfect squares would divide in. And whoops, sorry, we're seeing that nothing divides in, and so I'm going to be good to go, okay? But you can see all the way down here, nothing is dividing in. So we are good to go. This is going to be the correct answer. Now let's come down to the cosecant. Is there another way to do this for cosecant? Remember, I'm going to flip this. And we have a choice of how we do this. If we want, we can come back here to our original statement when we describe the two sides, and I can flip it. So it's called the reciprocal. So I have 3 square roots of 7 over the square root of 47. That's not a wrong mathematical statement. I just took the reciprocal, but it's not in correct form. So I'm going to take times 47 times 47, so I get 47 on the bottom, And I know that 7 times the square root of 47 is going to be the square root of 329. And I already know it can't be broken down. I already tried. I already took the perfect squares and divided all the way down, and nothing was able to simplify it. Let's go ahead and let's do tangent. Tangent is going to be opposite over adjacent. Opposite over adjacent. That's in correct form. There's no radical in the denominator. Let's jump down to cotangent, and we have 4 over the square root of 47. Again, here's the problem. We have a radical on the bottom. But there's a quick way of doing this. Remember, 4 square roots of 47 over 47. These two cannot be reduced, and I have it in final simplified form. We're on the third and final section of part 1 of right triangle trigonometry. So we want to solve for this missing side. So what I have to ask myself is, I have a given angle. I want to know, how would I describe this side? Would we say this is adjacent, opposite, or hypotenuse? Okay, so I have the adjacent side, and I know this is the hypotenuse side. Okay, so what one of our major trig functions, sine, cosine, or tangent, uses the terms adjacent and hypotenuse? Cosine. So I'm going to write that down. Cosine of an angle is adjacent over hypotenuse. And now let's put this in. We're working, by the way, right now, notice we're working with degrees, and the adjacent over the hypotenuse. In order to isolate for the x, I need to multiply both sides. Opposite of dividing is multiply, so I need to multiply both sides by 10. Then you're going to grab your calculator, and we're going to go up to mode, and we're going to make sure your mode is within degrees. So you're going to go mode. I'm going to do that one more time so you can see. Scroll down, go over to degrees, and press enter. And then I'm literally just going to plug it in like I see it. 10 times the cosine of 45. If you don't put it into degrees, you are going to get the wrong answer. Now let's round right now to the nearest hundredth. So x is approximately 7.07. Okay, our final example for part 3 of right triangle trigonometry. Let's first identify what we have. So from this angle, this is opposite. From this angle, this is adjacent. What major trig function uses opposite and adjacent? Tangent. So I'm going to write that down. Tangent of an angle is opposite over adjacent. So tangent of 20 degrees, opposite of this angle is 4, adjacent is x. Now this is a little bit trickier, but when I say trickier, it's just one more step. So we have a couple different ways we can go about solving this, and I want to show you 2 ways. Put your pencil or pen down. So I'm going to write this down, and you're going to choose which way makes most sense to you and which way do you think you can solve it the fastest. So here's one way. Notice that the difference between the first example in this section and the second example, do you see how the missing side was on top, and here the missing side is in the bottom? Do you see the difference? Okay, when the missing side is in the bottom, it's just a little more work, one more step. So here's one way. When the missing side's on the bottom, we could have the option for putting a 1 underneath our trigonometric statement, which is tangent of 20. Now I'm going to cross multiply. I have x times the tangent of 20 degrees equals 1 times 4 is 4. Now how do I isolate the x? I'm going to divide by the tangent of 20. Divide by the tangent of 20. Now x is by itself. I know my calculator is already in degrees. I'm going to go 4 divided by the tangent of 20, and x is approximately 10.98. Well, it'd be 9, so it's going to bump up. It's going to, oh, I told you just to round to the nearest hundredth. Sorry, this would be rounded to the nearest hundredth. Now, is there another way to think about this? There is another way you could think about this. This is my preferred method when the missing value is on the bottom, but here is another way. So ultimately, this x needs to be on top in order for us to solve. So it's being divided by right now. Let's multiply both sides by x. So I've multiplied both sides by x, and then I have x tangent of 20 degrees equals 4. How do I isolate the x? Well, they're being multiplied, so I'm going to divide by the tangent of 20, divide by the tangent of 20 degrees. Now x is by itself. I can plug this in. It's the exact same thing. We'll get the exact same statement. X is approximately 10.99 units long.